This lesson deals with Supplemental Problem 9.7. You can find this problem in the ECE202 ebook in the Chapter 9 Supplemental Problems on page 6. Let's use a Laplace transform to solve for the current I of t in the switching circuit, which we had worked on in ECE201 in Chapter 7. The input is a battery of 48 volts, the resistor was 280 ohms, the inductor was 100 millihenries, and the capacitor was 0.4 microfarads, and we had zero initial conditions. For the differential equation, once the switch closes, we have the rise in voltage is V in, the drop would be I times R, and the drop across here would be L di dt, and the drop across the capacitor is 1 over C integral of I dt plus the initial condition. Take a Laplace transform both sides of the equation. This becomes a step function of V in over S, R times I of S, and then our derivative property, this would become S times I of S minus the initial condition of I times L. And the Laplace transform of an integral is just simply 1 over S, so it's going to be I of S divided by S and then divided by C. And this is also a step function, so it'll be V sub C of 0 divided by S. But our initial conditions are 0, so it's just going to drop out. So you have V in over S is equal to I of S times R times SL and then times 1 over SC. And now solve for I of S. So I of S is equal to V in divided by S divided by this expression, which is SL plus R plus 1 over SC. Let's multiply numerator and denominator by SC. This then becomes S squared LC, SRC plus 1, and then we got the SC here in the numerator. The S's will cancel, and I'm left with Vn times C divided by S squared LC plus SCR plus 1. Vn was 48 volts, the capacitor was 0.4 microfarads, 100 millihenries, which is 0.1 henries, capacitor 0.4 micro, the value of C 0.4 micro, the resistor 280, and then the value of 1. So multiplying this out, I get 40 nano. This term becomes 112 micro, and then plus 1. Make the leading coefficient the highest power of S1, so let's pull out the 40 nano, and I'm left with an S squared. This quantity divided by 40 nano is 2.8K, and then 1 divided by 40 nano is 25 million. Take the numerator divided by 40 nano, I get 480. Because I have a second order denominator, let's take a look at using our forms in our table. This looks something like my damped sine wave, where I had beta over S plus alpha squared plus beta squared times a constant. Now let's multiply this out. I get S squared plus alpha times S times 2 plus alpha squared, and then I've got beta squared. So I'll put the alpha and beta squared together. Now comparing these two, this term here would be my 2 alpha. I could then solve for alpha, which would be equal to 2.8K divided by 2, or 1400. Okay, this term here needs to be equal to 25 million, so I could use this to extract for beta. If I take 25 million minus alpha squared, that would be equal to beta squared. I'll take the square root of that. And alpha is equal to 1400, so I'm going to square that. This turns out to be equal to 4,800. Okay, my numerator here is equal to 480, and that's equal to K times beta. But I know that beta is equal to 4,800, so I could then solve for K. K then would be equal to 480 divided by 4,800, or a tenth. I can then write I of S then as 0.1 times 4.8K over S plus alpha squared plus beta squared. That was, of course, our damped sine wave form. You can find the inverse Laplace transform of that using our table in 9.2. That's going to be equal to my scalar in front, which is 0.1. And then I have e to the minus alpha t, where alpha was 1.4K. Then I have the sine of beta times t, which is 4.8K. So I could write this then as 100 milli times e to the minus 1.4K, or I could write this as 1 over tau, where tau would be equal to the reciprocal of this, which would be 714 microseconds. So it would be minus t over 714 microseconds, or I can leave it this way too, times the sine of 4.8K times t, and the overall units would be amps, so we can multiply this by u of t, or just say this is valid for t greater than 0. This is the same result we found in the ECE201 ebook in Chapter 7 on the problem between pages 54 to 57. This is Supplemental Problem 9.7.